All right, we just used average velocities and limits to solve this problem about dropping a ball from the CN tower and trying to find the instantaneous velocity after 5 seconds. What I want to do is I want to show you what all of that means graphically. What an average velocity means graphically, what an instantaneous velocity means graphically, what the limit means, because I know that for some of you, this is the first time that you've seen the idea of a limit, and it may have gone right over your head. And so I want to look at it in a different way, because sometimes when we look at things from different viewpoints, one of them might make a little bit more sense, might help solidify things in our brain. So what I've done, we have actually two identical graphs, just one of them has a little bit more information on it. And so these graphs are the graph of the ball's position as a function of time. Now, it's a little bit weird. It looks like the ball's going upward. Position in this case is defined by how far the ball has fallen. So at 0 seconds, the ball has fallen 0 meters. But as time gets bigger, the ball has fallen more and more and more. And we know the position function is a quadratic function. So of course, the graph is going to be parabolic. The longer it has fallen, the more distance it has gone in a quadratic sort of a motion. So this is what the graph looks like, more or less. And what we want is we want to find the instantaneous velocity of a ball at a moment in time. Now, what we're going to do, instead of saying 5 seconds, we're just going to say at A. We're going to be looking at the point when time is A, because not every problem is going to be 5 seconds. We might want to look at 6 seconds or 3 seconds. So I just want to look at this generic point A. That's the moment in time that we want to focus on finding the instantaneous velocity. Now, we had said earlier that the average velocity was the change in position over the change in time. So if we look at an interval and we want to take the average velocity, so in this case, we're going to look at the interval from A to A plus H, so kind of H units further than where we started. Remember that the average velocity was the change in distance over the change in time. Now, this actually ends up being a known quantity. The change in distance is going to be the vertical difference between these points, because this is the distance axis, and the change is just that difference. So this is the change in the distance, and then the change in time is just how far apart we are on the time axis. And if we look at the change in distance over the change in time, that's basically the slope of the line between these points, right? The change in y over the change in x, that's slope, which you can see here. The secant line is a line that goes through a graph at 2 different points. And the average velocity on this interval is the slope of the secant line that goes through those 2 points, because the rise over the run gives us the change in distance over the change in time. And what we did, remember, in the last problem, we started by looking at the interval from 5 seconds to 10 seconds, but then we looked at an interval that was shorter. We looked from 5 seconds to 6 seconds. And when we do that, we end up with a different secant line. And then we looked at an even shorter interval. We looked from 5 seconds to 5.1 seconds. And it's a little bit harder to draw this, but we end up with another secant line. And each of these average velocities, when we're taking a smaller and smaller interval, is giving us the slope of a different secant line. And what's happening is these secant lines are getting closer and closer to the tangent line Remember, the tangent line is a line that touches a graph at a single point. And in the end, the slope of this line is what gives us the instantaneous velocity. But we don't have a nice way of calculating that. Finding the slope of a secant line is easy because we have 2 points and we can take the difference with the rise and the run. But with the tangent line, because it only touches at 1 point, we don't have a nice formula for that. So what we need to do is we need to take secant lines that use smaller and smaller intervals. And when we do that, what happens is the secant lines become closer and closer to the tangent line. And as we take that limit, if we look at the slopes of the secant lines, as we take the interval to be smaller and smaller, as this width gets smaller and smaller, the values that we get closer and closer and closer to the instantaneous velocity, to the slope of the tangent line, which we can't calculate because we don't have 2 points, so we can't do rise over run. If we use the same point twice, it would be 0 over 0, which is undefined. So this method of taking a limit allows us to take calculations that get closer and closer to a value that we couldn't calculate directly because it would be undefined, at least using the method that we have. So this is what I mean by a limit. We're looking at these values as this distance gets smaller and smaller, but we can never actually do the direct calculation where that interval has no width because we would have 0 in the denominator. So this is a way that we can use limits to figure out something that we couldn't otherwise calculate, if that makes sense. One of the big things about calculus is that it is the study of very, very, very tiny quantities, almost infinitesimally small. And this is your first example of how that works. And it takes a little bit of time to wrap your head around that, but hopefully with some more examples, with some more lessons, the more we look at it, the more comfortable you'll be with this idea.